Welcome, intrepid viewers. My name is Mr. Allshouse, and this is video 1 in the AP Chemistry podcast series. In this video, we'll be looking at naming ionic compounds in the systematic way. There are two main flavors that we need to learn about naming very early on. The first is ionic compounds. The second is going to be molecular or covalent compounds. In ionic compounds, we're going to have two ions. These are elements that have a positive or negative charge due to gaining or losing electrons. These two ions are going to be attracted to one another, one negative, one positive, to form a bond, just like two magnets being held together. In covalent bonds, which I'll cover in our next video, they actually share electrons. We see this in water. The hydrogen and the oxygens in water actually share an electron. Electron spins sometimes around the oxygen, sometimes around the hydrogen, but I'll leave that for another time. Ionic compounds are formed when we combine a cation, this is going to be positively charged, with an anion, which would be negatively charged, again like two magnets being pulled together. In most compounds, these are going to be electrically neutral overall, so I would have to have the same amount of positive charge on one side to cancel out the negative charge on the other side. Easy way to remember which one's which is a cation is going to be positively charged. The easy way to remember that is that the T in cat looks like a plus sign. Anions are negatively charged, and being like anti would be a negative end of it. In ionic compounds, these are primarily between a metal and a nonmetal. So when you see a metal and a nonmetal as a binary compound, a two-part compound, you will know that this is an ionic bond. The metal is going to be the cation, the nonmetal is going to be the anion. Occasionally these get swapped out for polyatomics, but that will be a later broadcast. So here we have a few examples where the first one's going to be the metal, second one's going to be the nonmetal. Seeing how this is my first video, I'll also point out that you always capitalize the first letter and you make a lowercase for the second and or third letter in rare occasions of any element. So an element always has the first letter capitalized and the second and third letter lowercase. These are for the abbreviations. Something that you should have learned in previous science classes, but it's a real key in chemistry that you, when you handwrite these out, that you make those distinguishable. When we're naming binary ionic compounds, we always name the cation, which would be the metal, first. And we name it by using its full regular name. The anion or nonmetal is going to be the root of the element followed by IDE if it's just a single element. If it's a polyatomic, then you name it for the name of the polyatomic. Let's go through an example. This is perhaps one of the most famous binary ionic compounds, and I use this as my first example because it's a good way of remembering the rules if you get lost. A lot of people know what this is called, and it's easy to remember, so you can use this formula to work backwards as well. Na is going to be the metal, Cl is the nonmetal. The metal should always be first, the nonmetal should always be second. Na, which is sodium, is actually a group 1 metal. It follows in that first column on the periodic table. You should always have a periodic table with you when you're doing any sort of chemistry, really. The cation formed from Na is going to be Na+. It's going to have a single positive charge. So here we have a periodic table. This is very similar to the one that you will be seeing on the AP Chemistry exam. Notice on here we do not have the names of the elements, but we do have their symbols. So you will need to remember how to go between the symbols to the names, or what names go with what symbols. Also, it doesn't have the famous staircase. Remember, the staircase is going to run from element 5 all the way down to element 84. On the staircase, we're going to separate metals from nonmetals. Everything that's to the left of the staircase is going to be a metal. Everything to the right of the staircase is going to be a nonmetal. Many things that touch the staircase are actually called metalloids. They're going to have some properties of either. Aluminum is going to be primarily considered a metal for most purposes. But we're not interested in aluminum yet. We're interested in sodium. Sodium is actually element number 11. We see it over here in this first column. Everything in this first column, except hydrogen in some cases, is going to form a +1 charge. +1. Get my plus sign looking a little bit better. The second column is going to form a +2. Everything down here in this little inset, these are going to be our transition metals, which also will have similar rules to these down here, our series. Over here, the next column will go and form a +3. Now as we get to carbon, remember the whole reason we're forming a plus or a minus is because the plus we're losing electrons in order to make it to this nobility state. It's a full outer shell. So sodium in its outer shell only has 1 electron, and it wants to get 8 electrons. It's easier to lose that 1 electron and have an outer shell similar to neon. Carbon, this column, has 4, and that's exactly half full. So most of the metals are actually going to lose up to 4 to make it all the way back around to the noble gases, while the nonmetals will tend sometimes to gain 4 to make it all the way to that noble gas state. The next column is actually going to form a -3. Oxygen is always going to be a -2, as well as everybody else in its column. And then our last column here is going to be -1. Fluorine, chlorine, bromine, iodine. So sodium is always going to form a +1, and we can see that quite quickly by looking at the periodic table. Chlorine is a group 7 metal, hence the ion of chlorine will actually be Cl -1. So remember our staircase. We find chlorine, and we know that everything in that column is always going to be a -1. Combining 2 ions to form a neutral compound, we have a +1 for sodium and a -1 for chlorine, so we only need 1 of each in order to form this compound. We then again name sodium for its name and chlorine for its ion name. We're going to take that beginning part of chlorine and add the IDE to the end, so we get sodium chloride, otherwise known as table salt. Let's look at another one. We're going to have aluminum and chlorine again. Aluminum is a metal, chlorine's a nonmetal. Aluminum is a group 13 metal. It's going to be right on that other side of the transition metals, so it's going to form a +3 charge. Chlorine is going to be a nonmetal, hence it's going to form a negative charge, and seeing how it's that group 17 again, it's going to form a -1 charge. Now we need to combine these to make a neutral compound. So we can use 1 aluminum, and that's going to be my +3. I'm going to need a -3 for that to combine with. Each chlorine is just going to be a single minus. So I'm actually going to need 3 chlorines. And you can see in my formula, this is denoted by this subscript 3. That 3 is telling me that there's 3 of the element before it. We will name this sodium chloride. I'm sorry, aluminum chloride. Sodium chloride was the previous example. We name aluminum for the metal, chloride for the chlorine with the IDE at the end. Now that was part A. There's also a part B to this. Anytime that you have a transition metal, many transition metals are capable of forming different charges. There's a few non-transition metals like lead that will also form different charges. But anytime we have a metal that's going to form different charges, we need to denote this. Iron, for example, can form a +2 charge and a +3 charge. It's swapping out electrons in its inner shells to try to make that outer shell more stable. Both FeO and Fe2O3 are valid compounds. Now if we use just the rules we learned before, FeO, we name the metal first, that would be iron. Then the O, which is oxygen, which becomes oxide when we add the IDE, we get iron oxide. If we look here, iron oxide. Both of these are called iron oxide correctly, except that we need to denote which one's which. Which one's the this iron versus that iron. So in order to do this in our system, we're going to go ahead and list the transition metal followed by a Roman numeral in parentheses. And while I'm not a stickler for this, officially you're not supposed to have a space between the metal and then the parentheses for the Roman numerals. So the Fe plus 2 is named iron 2, Roman numeral 2 in parentheses. When you say that, you just call it iron 2, but it would be iron open parentheses, Roman numeral 2 close parentheses. For this charge, we'll call it iron 3. This Roman numeral does not denote how many irons you have, nor does it denote how many of the nonmetal you have. This is a common mistake that a lot of people make at the beginning of the year. It's an easy one if you're not understanding where these Roman numerals come from. So, in this process, we're going to name the transition metal first with a Roman numeral in parentheses. That Roman numeral is going to be the charge of the cation. Then we name the anion the same way we did before, using its root and then IDE. So for my first example, I have FeO. I know that oxygen is always going to be a negative 2 charge because of the column that's in. There are a few times that we get peroxides, but that'll be a later show again. This iron then is going to have to be a plus 2 charge. I know it's a plus 2 charge because there's only one iron to equal out to my one oxygen. My oxygen being a negative 2, my iron has to be a positive 2. So I call this iron 2 oxide. Remember that 2 is denoting the positive charge there. As a side note, I am writing these charges here to help us try to keep straight, but when you answer a question, you don't want to leave the charges in your final answer. That's actually going to say that they're two separate ions floating around in a solution or in a gas, not combined together to make a compound. Here we have Fe2O3. Oxygen is going to be negative 2. We have 3 of those, so we have a total charge of negative 6. That means that the iron is going to have to be a plus 6. Now, we have 2 irons to make this plus 6, so together they make a plus 6. Each iron then is going to bring a plus 3 to the party. This is called now iron 3 oxide. Iron oxide is also known as rust to everybody outside of chemistry. Here we have a few examples. Go ahead, pause the video and work through it. Already have the negative 2 written there on oxygen to help remind you. When you're done, start up again and we'll go over these. Hopefully everybody worked through these. We'll see if you got them right. The first one is going to be copper 2 oxide. Remember, copper is a transition metal, so you're going to need to add that Roman numeral. The next one is going to be sodium iodide. Take iodine, and you take off the N, you put iodide. The next one is going to be lead 4 sulfide. Then we're going to have lead 2 chloride. Remember, these Roman numerals is not telling me how many leads I have, nor how many of the nonmetal I have. For the next one, we get silver oxide. Now this one was a little bit of a trick question. Silver is one of the rare exceptions that a transition metal is not going to form multiple ions, so you really don't need the Roman numerals there. And then the last example I have here, going to be magnesium nitride. Now I can go the other direction and give you a formula, and then we can work out the name. So we got barium bromide. Bromide, and I usually like to start with the second or the anion, the nonmetal first, because that can help me work out what the metal is, especially for the transition metal. Bromide is an ion of bromine. This is going to be Br. It forms a -1 charge. Barium is Ba. It forms a +2 charge. Remember that our formula must be electronically neutral. Our positives need to cancel out our negatives. This will leave me with one barium, which is a +2 charge, and two of my bromides, which are going to be a -1 charge each. Two of them will give me a -2 charge. For copper 2 iodide, we're going to take the anion first. We know that symbol is going to be I. It forms a -1 charge. Then we go with copper, that's going to be Cu for its abbreviation. And this we know is going to be the +2 variety of copper. Copper can form more than one type of cation, but because we see the Roman numeral 2 here, we know that's going to be the +2 variety. We must make these electronically neutral. We have a +2 and a -1. We need two of the -1s to equal the 1 + 2. So we get CuI2. Here we have a couple more examples of finding the formula from the name. Go ahead, pause the video, work through each one of these, and we'll come back. Okay, let's take a look at the first one. Iron is going to be Fe, chlorine is going to be Cl. Chlorine is always going to be a -1 ion. Iron here is going to be a +3 ion. So I know I'm going to need 3 chlorines for every 1 +3 iron I have. So I get FeCl3. For iron 2 iodide, I'm going to get FeI2. Mercury 1 chloride, HgCl. Potassium iodide, Ki. Zinc chloride, we're going to get ZnCl2. Remember that zinc is always going to form a +2 charge. Cl2 is going to form Cl is going to be a -1 charge. Two of those will give me a -2 charge. Lead 2 sulfide is going to be PbS. Remember that this number here is not going to be how many I have of it or how many I have in my second one, but rather what its charge is. We see this very clearly in our next example. Well, it's going to be Cu3N2. And that tends to throw a few people off, so let's work through that one. Copper is Cu. Nitride is from nitrogen, which is going to be N. Nitrogen will always form a -3 charge. This copper is going to be a +2 charge. In order to make these equal, we have to find a common denominator between the two of these, which is going to be 6. So we're going to have 3 + 2 charges and 2 -3 charges. So we end up with 3 coppers and 2 nitrogens. Well, I hope you found this video on naming ionic compounds helpful, and I hope to see you back here again.